举个手，谢谢，谢谢，谢谢。好，那我们就开始吧。Okay. All right. So welcome. Good morning. So as you know, you might know, next week will be our midterm 2, and next week will be the. Let me take a look. Next week will be a sports event in our campus, right? So it will have no class, but because the 18 weeks has been reduced to 16 weeks. So I guess I cannot afford to stop the course. So I will upload my video just like last few weeks. Yeah, it will be around like chapter 8. Chapter 8, okay?
这是我在网络上找到的。Thanks to 六庭 with so X I cannot for the set 吸收。I will go over my video。就是来拉给 Vicky 相关结果，请看。
Okay. 好，嗨。Okay, so let's just write down how to write it. Maybe I just write down at 7th, okay? Hey. So next week will be 29th of November. It will be midterm 2. And the PDF 4, 5, 6, okay? And the next week, 6th of December, no lecture, no physical lecture, lecture. And video will be upload just like last time, okay? So if any question, just email me, all right? Yeah, I have received some problem from students, and I try my best to solve it. So if you have any questions, just email me and teaching assistant, okay? So let's 29th of November, midterm 2, PDF 4, 5, 6, and 6th of December, no physical lecture, video will be uploaded. I should make it a proper sentence. End. OK， 好，那不用中文翻译吧哈，那就这样，有问题了赶快 email 给我。好。对，然后我发现只要有 video upload， 整个就是课堂就会比较轻松一点，好，我们就可以 take our pace。不然的话，我后来去发现我以前的录影，就是我以前上课的步调就比较慢，因为有18周，结果因为前阵子就是变成16周，然后就开始步调越来越快，我就很紧张啊。那今天就发现了这一招，可以上传影片的话，当然这是我第一次做，所以我可能未来几年，我可能会好好的把这2次的课程录好，这样子，或许吧，有空的话，好 ，OK。 最近天气好奇怪啊，有时候好冷，有时候好热。OK， 好，那 so that's it. Please let all your friends in this class know this. Okay. Otherwise, yeah, maybe some students may not attend this course or didn't watch the video, and then some problem occurred. All right, so let's go back to our lecture. So last time we talked about the summary. Yes, we have Boltzmann, Maxwell-Boltzmann, Fermi-Dirac, and Bose-Einstein, each of which has their own application for different materials. Okay, for example, Maxwell-Boltzmann is for ideal gas, dilute gas. The feature will be Mj is much less than Gj. So they have plenty of choices. Okay? And the statics means that because we examine the material's behavior, so we write down the possibility, and we write down all the possibility, and then we solve natural log W, and then we come up a solution. Nj over Gj need to be in list form. Otherwise, it will not stable. Okay, Nj over Gj will make the W maxima, which means that you always, when you pick up the value, pick up the case, you always take the equilibrium stable state because this maxima possibility, maxima probable. Okay. And also because the
N Apple 网站应该可以回答这个问题，还可以提供你更多资讯。
怎么办？我要如何去把 Siri 关掉？真的很烦。左上角这个系统，第二个这个，耶、yeah, 谢谢你。好，我记得我关过，然后它可能什么更新过后啊，什么又出现了。谢谢。好 ，OK, continue. Okay, so maximize the natural log. Maximize the natural log W, which means that maximize W. Okay, that's it. And the Boltzmann statics suitable for solids and some liquids, and very direct suitable for fermion, of course, and for the study of the free electrons in metals or semiconductor. Bose-Einstein for photon or some laser things. And Maxwell, yeah, ideal gas, good. And then we try to figure out the term of the difference. The term of difference is that if you heat up, you will change the distribution of the particles. But if you change give the work, change the volume, it will alter or change the energy level of each level. And then we found out the correlation between chemical potential and alpha constant, which we want to determine. And there's a really important point is that the mu here is different from the chapter 9 mu in chapter 9, because chapter 9 is for kilomole, but now because we're focused on particle base. So this mu is related to 1 per particle. So mu equal to the mu in chapter 9 divided by MA. Okay, and then we notice that we can determine alpha and mu, and then by following procedure. And you've noticed that if we use Maxwell-Boltzmann static, start from Maxwell-Boltzmann statics, we can show that the S equal to this, and F equal to that, and mu equal to that. And please don't memorize it. Okay, you need to understand how we derive them, how the procedure. Okay, we apply the classical thermodynamics theory to obtain these results, but shouldn't apply to all the statics because we start from Maxwell-Boltzmann statics. Okay, so in the exam or in the your homework or practice, sometimes they will ask you to use different statics to obtain S, F, U, mu. Some of them will different. Some of them will the same. They will be the same. So you need to be careful. Okay? Yeah. Now let's compare a bit about the distribution of the statistics. So Fermi direct, Bose-Einstein, and Maxwell-Boltzmann distribution. Okay, so let's plot the energy, the mj over gj, the ratio. Okay, because you can see we have different temperature. So this is actually the variables. They will change over maybe temperature or over the material you choose, mu, right? So we set this as a, we set this this one as an x, okay, using as an x and make it a x-axis, and y is mj over gj is the result. So let's take a look how x varies and affect the ratio between mj over gj. Okay, so first of all, you can imagine that you have a you can plot the x by using Excel. You found that it will look like that and that and that. And another part is that this is BE. This is another part for BE. Okay. However, I mean mathematically, if you just apply this formulation, then you can get this and that for BE. But why I didn't show this? Because you can see that the y-axis is the ratio between nj over gj. So the nj over gj and the gj, actually the first one is a particle number. The other will be the choices, right? Degeneracy. So they will definitely always greater than 0. So this part means that the y is negative, which means that it's physically impossible. So you can see that this is mathematic models to describe the material, but some part of it may not suitable for real life. Okay, so this is not probable. Okay, so yeah, that's it. And then we notice that BE, MB, FD, yes, they converge when X become greater and greater. So you can see that, right? NJ over GJ become, GJ is much greater than NJ, so makes the Y value close to 0, approaching to the 0. So you see it's really big, and so it make this value become close to 0. Okay, right, that's it. And also because this x become very big, so which means that exponential become very big, and big number compared to a, it should be 1 or -1. So a will be negligible when this one going to really right hand side to the x become really big. So in this stage, the MI, well, it should NJ, okay, it doesn't matter. MJ is much less than GJ, and so which means that A is not effective and Y is approximated to exponential minus X, and the energy increases. As energy increases, MJ much greater, much less than GJ, and go that way. Okay, right. And then we can notice that when X become very small, close to zero, the BE distribution will become really high, right? So okay, anyway, so this part is that when the X close to zero, the particle condense in the lower energy state. Yes, they will just condense everything there. So you can see MJ is MJ is become greater and greater, okay, compared to GJ. So the ratio become higher. Okay, and then to see FD. FD is a little bit interesting. FD here, it will looks like the okay, and if you just using Excel to plot this, you can see the line like this, and this is really interesting. You can see when the when epsilon j minus mu less than 0, which means that your energy level become very low, and the mu become greater than epsilon j, so it become, and then you can see that here they will have they become 1. They become 1. Exponential x is going to 0, so it becomes 1/1. So the FD become 1. Okay, which means that 1 particle per, this part indicating 1 particle per state uniformly. You can see here MJ over GJ the ratio become 1, which means that in this state, 1 particle for 1 degeneracy. Okay, this is really interesting. Once again, this is the mathematical model. We need to not necessarily means that there's materials in the real world fit this, but because this is kind of extremely case, and this is extremely case. So not all the cases will fit to the reality, but we're just going to introduce how the distribution looks like in the mathematical model. Okay, so if you want to see the distribution, the behavior of the 3 distribution, you are welcome to see this website, and it will has the evolution of these 3 lines, and then based on different temperature. Okay, it will change their shape. Right, and also you will find that MB will always in between BE and FD. OK， 好，那我们接下来讲就是我们来比较一下这3个线。好，这3个线其实就是用 Excel 去画而已啦，哈，就把这个东西画出来。我们用这个黄色的部分当做 X， 然后 Y 的话就是这个值。OK， 然后我们就会发现呢，如果是 BE 的话，哈 ，BE 的话它画出来的时候其实会有2条这样的线。那但是我们为什么不画这个？原因是因为 NJ over GJ 都是大于0的，它不可能会有 ratio 会是负的啊，所以这边是不可能的现象。但是我 我们这边可以告诉大家，就是说这3条线其实是科学家用数学模型试图去解释现实生活中的材料，所以不一定会是完美的。那所以说像这个地方就是不完美，不可能会在现实中生活中出现这样子。那当然啦，就是等于是说在大部分的状况下是适用的，但是可能在极端的状况下就不适用了这样子。好，那这边就可以看到这边有问题，然后接下来看到如果今天就是能量越高啊，就是 epsilon j 就是应该说 x 值越大了哈，能量越高嘛哈，它就越大的时候，你就会发现 x 呢就这3条线都趋近于越来越小，那也就是说 nj over gj 是gj 会远大于 nj 的意思。那这也就是为什么 b 跟 fd 跟 mb 就会收敛在一个值上哦。当我们是很高能量的状态下的时候，好，然后就是还有什么哦？然后我们可以看到 B 这条线呢，如果在能量比较低的状态下的时候，应该说 X 比较低的时候，那它就会就是倾向聚集在 low energy state 的状态。OK， 好，然后我看还有什么呢？哦，对啊，你看为什么这边是0呢？就是它 x 趋近于0的时候，表示说这个 t 越来越大嘛。好，然后等一下我想看 t 越来越大，趋近于 t 越来越大，对，t 越来越大，为什么会是 low energy state？好奇怪，怎么我自己卡住了？等一下我想一下哦。哦，不好意思 ，t 是定值 ，sorry，t 是定值，好 ，t 是定值，然后 epsilon j 就是energy level 这边是 energy level j 是决定这边的位置啦，这边的位置，然后所以说它能量越小，减掉 mu，t 是给定的一个值，对，t 是给定的一个值 ，t 没有在变，好 ，t 没有在变，然后 epsilon j 越小的话，它就 exponential x， 它越小，反正这个值就越小嘛，越小 x 就越小 ，x 就越小，就在这里。然后带进去这里的话，哦，等一下，越小它是减1，哦，它减1，然后它越小，不好意思，我卡住了，对，0越小的话 ，exponential 很小的话，它就会很小，没错，然后它是-1，耶，我记起来了，好，对不起哈，OK，好，那因为这边x 啊哈，如果越来越靠近0的时候，越靠近0就是 exponential 0啦，exponential 0的话就是1嘛，那1减1就会接近于0，所以说它这边接近于0的话，它就会爆炸，对，好，对，终于想起来了，好，很好，那总之就是 energy level 这边越小的时候，它这边的减1嘛，1减1会靠近0。那越靠近0的话，其实表示说这个分母越小，它的nj over gj 就会越大，表示说它会 nj 就是比 gj 还要大很多很多，也就是说它能接比较低的时候，大部分都会去聚集在 nj 就是聚集在低的状态下，低能接的状态下。OK， 好，不好意思，刚刚忽然卡住了，就想说，为什么？因为我刚刚以为 temperature 其实没有。temperature 这个值啊，在这张图是固定的，好，因为如果你画出这条线的时候，你的 temperature 一定是固定的。那如果你去改 temperature 的话，我们之后可以去看，你下课的时候可以去看这个网页的资讯，它就是改变 temperature，然后这几条线就会开始变化， 好，所以当你画这条线的时候，这个温度已经是 fix 住的了。所以你可以看到，我刚刚解释不应该去解释 temperature 会变。好，那我不知道这边可不可以点，不能。好，那没关系，总之你可以去点点看，这个温度它会随着温度去画这3张图。好，画这3张图。Okay, sorry, I just stopped. I just want to say, mention that the figure we plot at this moment is that the temperature is fixed. Okay, if you change the temperature, the position of these 3 lines will change. Okay, so if we want to discuss this plot, typically we're just considering the higher energy level and lower energy level situation. Okay, so this is when we change the x, just discussing the epsilon level, J, lower or higher. Okay, we are not discussing changing the temperature. Okay, because the temperature will fix the position of the line. And if you want to change your temperature, please see the website I provide here. Okay, sorry. 好，大概是这样子。但是它的那个行为啦，哈，大概就是这3条线的，我们这个页的目的就是想要告诉大家这3条线每个位置它所代表的意义是什么。好，那这个位置的意义是跟它的 energy level 有关，跟它的 temperature 是没有关系的。OK， 好，在这张图里面它已经 fix 住了。OK， 好，谢谢。Right, so next let's practice one example. The example is that calculating the thermodynamic probability WK and each macro state and the average occupation number of each. So please calculate all the possibility of the WK, okay, and where we will setting the system limitation. Total particle number 5 and the total energy 12 epsilon. And energy of each energy level is epsilon J equal to J epsilon, which means that when you have 4 energy level, the 4th energy level, you have 4 epsilon. Okay, so the epsilon here is the kind of unit provided in this problem. So the degeneracy of level are G1 equal to 1, 3, 4, 5. Okay, so you can notice that only 4 level of the are given in this problem. So you see, the reason why we didn't consider higher energy level is that only 4 energy level are given in this problem. So of course, again, this is a toy model, because if we just apply a real world model, sorry, we cannot using our hand to calculate that. So only 4 level, and this is a toy, only have 12 epsilon energy, total energy. Okay, so if this system apply to Bose-Einstein or Fermi-Dirac or Boltzmann-Einstein, Boltzmann statistic, what will it be? What will the WK will be? Okay, so we can imagine that, right, this is just some material related to boson and some related to fermion, some related to solid, something like that. Okay, so first of all, this problem is really important. You must see that in your midterm too. So please do more practicing. Okay, you need to be really, really careful. If you don't have your table correct, you will have all wrong, and then it will cause this score. I mean, this problem will just become very, harmful for your score. Okay, so be careful and be just practice more. Okay, so now they ask Bose-Einstein, Fermi-Dirac, and Boltzmann statistics. Okay, so there's one trick here I will need to provide to you. Please always, no matter how the order of it, maybe the problem asks you Fermi-Dirac first or Boltzmann statistics first. please always start from both instance. Okay? The reason I will let you know later. Okay? So now let's firstly start both instance. The first one, BE, the W need to be write down like this. J Nj plus Gj minus 1 factorial. Nj factorial Gj minus 1 factorial. Okay, so this is both instance W looks like, right? And I want to write down W1, W2, sorry. W2. Okay, so and continue. Okay, so what will we be? What is N1, G1? So we need to have a list here. Okay, so let's list. So K equal to 1, 2, 3, 4, 5, 6. So this is actually we don't know in the beginning, but we know that the energy level 4, 3, 2, 1 level, and each energy is epsilon J divided by epsilon. What does that mean? Epsilon J equal to 4 epsilon, 3 epsilon, 2 epsilon, epsilon. Okay, so each energy level looks like that. Then we are going to distribute the 5 particle to make the 5 particle in all these energy level and have total energy become 12. Okay, so the tricks here is that we always start from the highest energy level to make it everything simpler. Okay, so firstly 4 and 2. So we place 2 particles in the highest energy level. Can we put 4? No. 4 times 4 becomes 16. It exceeds 12, right? And then if you place 3, no, because 3 times 4 becomes 12. Okay, it's just 12. But how about the other 2 particles? No. So the only choice is 2, right? So you have 2 times 4 become 8. So you have 4 left, okay? And then you can put 1 in 2, the 2 in 1, and then summing up become 12, okay? So this is the only way. If you put 2 here, you only can put 1 and 2 here to make it 12, right? So this is the first case. The second case is that, okay, you start put 1 in the highest level, and then you start put 2 in the third level. Okay, so 1, 2. It's become 4 and 6. So you got 10, and then 2 energy unit left. So you can only put 2. You shouldn't put here 1 because there are another 1 particle you have nothing to play, no level for the remaining 1. So you only have only one choice is put 2 in the energy level 1. Okay, so now 2, 1, and then you can put 1, and then you reduce 1 a bit, and you put the highest level. So more particles in the highest level at the moment. Okay, so 2, and then you put all this list, and you reduce the third one, become 4. Okay, so you do this every time, and then to make it all possibility list in the table. So I believe after you do this systematically, you can always you see reduce. I mean 2, 1, 1, 1, 0, 0, and because of this, you start to reduce that, and then although because this becomes 0, so you can up become 3 again, and then you reduce, and here reduce. Okay, so start to reduce the highest energy level and try to combine come up all the permutation of these distribution. Right. So after you do that, and then you start to see energy level 1. Sorry, not energy level 1. W1, the first choice. The first choice will be 2 plus 5 minus 1 factorial and divide by 2 factorial 5 minus 1 factorial. How? You see 2 and 5, okay? And the other will be 0, so you just skip that, and it's 1, 3, 2, 1, okay? So you can imagine what will it be for the next 1 plus 3 minus 1 factorial. So you can see this is really a labor work. And you need to be really careful about this. Otherwise, you will lose a lot of points in this problem in your midterm. And this is simple, I guess. All you need to do is be careful. 45. So that's how we get 45 here. Okay? And next, W2. W2 is easy because it's 1 plus 5 minus 1 factorial. 1 factorial 5 minus 1 factorial times 2 plus 4 minus 1 factorial. 2 factorial 4 minus 1 factorial times 2 factorial 0 factorial 2 plus 1 minus 1 factorial equal to 50. So 50. All right. Right. So that's it. And then if you want to find the average occupation, it will be mj equal to 1 over omega. Omega is the sum over everything, right? Sigma k n j k times w k. So it's kind of expected value. Don't forget this. And yeah, so you see all these summation together become 450. And the occupation for this will be 0.744. I mean, you can calculate through this and then get this one. Okay, so you can have n bar with this equation. Okay, so that's it. That's it. So it's easy, right? But it's tedious. Okay, it's cumbersome. You need to pay a lot of attention to write it down, but it's easy. OK， 好，这一页很重要，就是题目一定会出在 midterm 里面，期中考里面，不一定，当然不一定是这一题啊哈，那它一定就是要希望你去把所有的 case 都列出来。那这一题呢，就是需要大家的耐心跟细心，因为这很简单，但是如果你错一个地方，你就完蛋了。就全错，就会全错哦，所以真的要非常小心。那多练习，有耐心，多检查，好吗？好，那这边还有一个重点就是我先讲题目好了，他就是说要你算thermodynamic probability嘛哈，然后他规定说这个系统有5颗，然后它的总能量有12个单位 ，epsilon 是一个能量单位，然后它每个能量阶是第一阶就会有1个 epsilon， 第二阶就有2个 epsilon， 这样上去，然后它给了 G1、G2、G 到 G4， 好的 degeneracy 在这里。好，那为什么不看5呢？因为他没告诉我们。好，所以说我们就只算4 level 就好了。然后还有一件事情就是，对啊，就是比较 这是玩具嘛，哈，那如果是真实的话，你根本算不完，啊，所以只能是玩具，那就只弄了4个 level。好，那这时候呢，还要你算，如果今天这个材料是适合用 Bose-Einstein 来算的话，它会怎么样？如果这个材料适合 Fermi Dirac 的话，它要怎么算 ？Boltzmann statics 的话，它要怎么算？好，那这边有一个技巧，就是说，当这个题目如果先问 Fermi Dirac，先问 Boltzmann 的话，然后再问 Bose-Einstein 的话，不管它，你要先算 Bose-Einstein。原因是什么？我等下会告诉大家。好，那我们就先算 Bose-Einstein，然后呢，我们就来看 Bose-Einstein 的 W 长这样子，这边我们之前都推导过咯。然后接下来我们就开始算如何去排列这个值，而且是每一个颗粒都要有 energy level， 你不能把一个 energy 不要把一个 particle 丢掉哦，它一定要占据哦哈。所以说你不能一开始就把这边放3进去，3、4、12，对，它满足啦，但是还有一颗你没有放啊，它也没有 energy level 等于0的地方嘛哈，所以说你不能这样放。所以呢，我们这边的技巧就是尽量塞满最高能量的。这样子，那我刚刚塞4不可能爆了，塞3也不可能，那塞2，好，塞2的话呢，你就可以继续这样排下去，那也只有一种解法，你自己排排看。然后接下来就是剩下1个，那接下来下面就会有一些排法，一样，剩下1个的时候，一样我会是尽量去把第2高的排满，然后能排多少就排多少，然后去看下面可不可以算。所以就这样子一一这样排下来，所以你看21110，好，所以你看到最高等级就是一直在往下递减就对了。然后你也是一样，递减完以后，你就尽量去塞第2高等级的，就这样，那这样塞下去，你就可以得到这6组解。好，6组解完以后呢，我们就把这边的2跟5带进去，1跟3带进去，啊，当然这边是0啊，所以没有在这边哈。然后2跟1再带进去。就可以得到45，然后你每一个都要算，算完以后呢，你就可以得到这下面这个东西，那你就可以得到 W，不对 ，omega 全部加起来，W 全部加起来就是 omega 算出来之后450，这时候你就可以去算它的那叫什么average occupation number， 也就是它的期望值啦哈，每一个个数乘上它自己的几率，然后加总起来就是这样，OK， 好，这样听懂了哈。好，这题很简单，但是很麻烦。接下来才是重点。Next one, this problem here is really important now because the reason why we are going to always do Bose-Einstein is because it's combining the most case. The reason why so next we are going to get Fermi Dirac. Okay, how can we get Fermi Dirac table? Easy. The reason why, the Fermi Dirac is that fermion cannot share the same particle with degeneracy, right? For one degeneracy. So which means that in this case, this is not allowed. Why? Because degeneracy is less than particle. Okay, the one cannot share by 2 particles. Okay, so no, not this. How about here? No, again. Dang. How about this one? Okay. How about that one? No. How about this one? Okay. This one? Okay. All right. So, not suitable for FD. Okay? So you can delete the not suitable set for FD. So then you can immediately get the table for Fermi direct. Okay, so the reason why we always do Bose-Einstein first because they are more general, because they can share the same degeneracy with particles, right? But Fermi direct doesn't. So you can delete them, and then you get straightly the obtain the table. OK， 好，这边蛮重要的哦，就是先算Bose-Einstein，然后你会发现 Fermi direct 是不能跟它的 energy level 是degeneracy 是不能分享的嘛，好，所以只要我们 degeneracy 小于你的 particle 的 number， 那就表示不行，所以就把它划掉就好了。划掉以后，剩下的就是适合 FD 的 distribution， 所以你就直接把那3行第3个 case、第5个 case、第6个 case 拿过来到下一页就可以了。Okay, so FD only have 3 available cases: the 3rd column, 5th column, and 6th column. And then you copy these 3 columns in the next page, and then all done. Okay, so that's the reason why we are not using. We come first for Bose-Einstein. So if this is okay, let's proceed to the next page. So the WFD equal to pi j nj factorial gj minus mj factorial gj. And yeah, W1 equal to 5 factorial 1 factorial 4 factorial times 1 3 4 factorial 2 1 3 1 2 1 equal to 5 4 3 1 60. Okay, so that's the reason why we have 60 here. Okay, right, so you continue and then you can get the same thing. Right, easy. Right, so the Boltzmann statistics, again the same. WB n factorial pi gj nj factorial, so you can have W1 equal to 5 factorial 5 to 2 factorial times 3 1 1 factorial 1 2 2 factorial 2 2 5 0. Oh, by the way, the B here doesn't have the this is an ideal guess, right? Sorry. It's distinguishable and they can share, right? They can share degeneracy, so this is still okay. So just copy the Bose-Einstein, and then you can just apply different WB, and you can get your W1, W2, okay? So again, that's it. 好，基本上最重要的就是 FD 是要把它划掉就对了，把 G 大于 N 的划掉就可以了，你就得到 FD 的 table， 你就 apply 这个式子就可以得到它的每一个数字了。那 B 的话你就也没这个问题，直接沿用 Boltzmann-Einstein 的式子，不是 table， 然后表格啦哈，然后这边就 WB 带不同的就可以得到这样。所以基本上 Boltzmann 跟 Boltzmann-Einstein 其实是两个是 Bose-Einstein 其实是一样的 table， 但是带的式子不一样，就这样而已。 Okay, that's it. So we finished the PDF 6, and then we will have 20 minutes break. Sorry for the late 2 minutes for your break. Sorry. See you later. Well, I will see you 12 past 10. If you have any questions, let me know. 哇，这样全错，我哪里做错了？哪里啊？哎，是0哈。
对。
好，谢谢大家。那来排队吧。哎，
那这里少写个结。
确实。
没事哦。哎，真的耶。好，那来吧，大家都写个加分吧。这里，开始。109。你自己写。你可以到这边来。哎呦，好笑！一下课全部大家冲过来，我哪里错了？
我领导了。
哎，请说。
那个第一阶这个最高不能放3颗是原因，因为上课就会。
因为它3、4、12嘛，就12就满了。
对啊。
那剩下两不就5颗吗？那剩下2颗要放到哪？就无法放了，因为没有 energy level 0这个东西，所以。哎，请说。
这一节的最大值为什么是6？
哪一个？
便宜的。
没有，这个1、2、3、4、5、6的6其实是数字的意思，就是它只是你这边有6个 case， 如果你今天有7个 case， 这边就会变7、8、9，所以那个数字其实是没有意义的。
哦，了解。
哎，这个数字没有意义。你如果今天是从另外一个方式去排这个 table 的话，它可能是这边是6，这边是2。
哦，
对，这只是编号而已。
哦，了解。
哎，对，
了解。
对。它跟能量大小其实没有关系。
好。
26页。请说。
如果是从到 D 的话，那第3阶为什么是0？
好，如果你说第一个 case 吗？
对。
第一个 case 啊。
对。
第一个 case 如果今天是2的话，2、4的8，对不对？8的话，那如果你今天你还剩多少？还剩5嘛？不对，
总共是
12嘛，所以是4，对，你还剩4。那这时候如果你今天要填1在这里的话，
对，
你就只剩1了，对不对？
哦。
那你1的话还剩2颗，那你就有1颗会变成没地方放。
哦。
因为你没有 energy level 等于0的这个地方。
哦。
就是它就爆了，这样。
喂，老师，老师好像没有开麦克风。
Okay, thank you very much. Thank you for
老
your
师，
听得到吗？嗨，
可以，
哦，
可以，可以。
谢谢。哇，他自己关呢，不好意思，真是不好意思。总之我刚刚在聊天啦，没什么关系。诶，那这样他等一下就录不到了。Anyway, just saying that there's we have we just re-announce this two important events and just talk about the Facebook made out of fashion. Just talking about that. Okay, nothing important. Right, so let's continue our lecture. Okay, thermodynamics property and partition function Z. Partition function Z is really important when we firstly derive Z. And maybe at that point we don't know why it is so important. But today, at this moment, you will notice that Z is really important. Z is really important. Okay, so when in this PDF 6, we have derived from Maxwell-Boltzmann distribution, we found that for a dilute or ideal gas, we have S equal to this, and of course it will be written by Z. F also written by Z. Mu written by Z. Okay, so Z is really important, you know that. And Z looks like this. And it's also, as you can see, this is a bridge between statistical and classical thermodynamics, right? And then we just continue to obtain more properties that we are familiar with. The first one is internal energy. So the internal energy, you see U equal to summation Nj epsilon J. So you have Nj equal to what? You know Nj over Gj equal to this, right? For the Maxwell-Boltzmann distribution. Okay, so because we are going to have summation of Nj, so why not we just put the Gj to the right hand side and put summation. Sorry, I should put summation here, and then we can obtain this part. Okay, so that's what we are going to do. That's it. So summation Jnj equal to m divided by z. I don't know, Gj exponential minus epsilon j over kt. Okay, so if we have this, what we've written here, and we substitute to the nj, and then we can get u equal to okay, that's it. Easy. 好，我们刚刚讲到就是 partition function z， 之前我们在算出来的时候，我们就说很重要，但是我们当时却不知道为什么它很重要。后来我们就上一章 PDF 6的时候，我们就找到 OK Maxwell-Boltzmann distribution 的话呢，我们的 S 是连接统计热力学跟古典热力学的桥梁。我们把 Z 带进去以后，就发现哦 S 会等于这个东西 ，F 会等于这个东西 ，mu 等于这个东西。哦，所以我们的 material properties， 我们最常见的材料性质都可以用 Z 来写，好，用 Z 来写。那这时候我们就继续下去了，好，第7章就开始继续把它就是发扬光大。那我们的 U 就开始看啊 ，U 的定义其实很简单，就是把每一个能接的 particle 乘上它自己的能量，然后把它加总起来嘛，就是它总内能，所以它其实的定义就是长这样子。那这边呢，NJ 怎么办呢？我们有 NJ over GJ 在 Maxwell-Boltzmann distribution 的时候，它会长这个样子。那要怎么样得到这个呢？就把 GJ 抵过去，再加一个 summation 就好啦。得到这个以后，加进去就可以得到这个东西。好，也就是说 U 还是一样可以用 Z 来代表。OK， 好，那大家有没有发现我刚刚讲的就是这个 NJ over GJ 这个东西，我说是 Maxwell-Boltzmann distribution 的时候写出来的。我既然讲这句话，表示说也有可能，请大家在算这些东西的时候，不是 Maxwell-Boltzmann statistics， 可能是别的，好，可能是别的东西。那别的东西的话呢，这边长得都不一样。当然，这个东西也长不一样。那这个东西不一样的话，你带进去的东西也会不一样。好，所以说千万不要记。好，如果今天题目是给别的 distribution， 你要小心，不能直接把这个东西直接硬背把它带下去，这是不对的。好，要小心哦。Okay, one thing I need to re-emphasize because I mentioned emphasized before, but today I still need to emphasize a bit again because as I mentioned, I always say, okay, this formulation is based on Maxwell-Boltzmann distribution. These MJ over GJ, these things, is also based on Maxwell-Boltzmann distribution. So please don't memorizing all these. Don't memorize it. You need to understand how you obtain that. Okay? So if the problem asks you other distribution, please don't use this. You need to follow the same procedure to get the equation, the formulation for that particular distribution. Okay? So don't memorize it. Next. So continue, partition function Z for other thermodynamic probability. So internal energy looks like this, right? Still a little bit ugly. So can we refine that? Let's take a look. Yeah, you can see that still ugly, but compared to the Z function, don't you think they are quite similar? Don't you think they are quite similar? GJ, summation, GJ, epsilon JKT, epsilon JKT. They look really, really similar, but the only difference is that epsilon J and here, nothing here, right? So all we need to do is we try to make this epsilon J jump to the front, right? So how can we do that? So this part, we want to get rid of that. That's because it's ugly, right? So we just do the differentiation for this. We do differentiation so the epsilon J can jump to the front. Okay? So yeah, that's it. So we jump. That's the result. And we take the KT square over 1 over KT square to the outside of the summation because they are constant, and then we found that we successfully get this. Okay, this and that are the same, so we can replace that and we can substitute that here. And and also epsilon J is a function of V when V is a constant, right? So which means that you don't need to differentiate that. So you can, if epsilon J is a function of V, and if you do the differentiation, you need to do extra term. But if you set V as a constant, so it will be easier, okay? And then you can get this, directly substitute that here into here, and then you can get, immediately you can get U equal to NKT square natural log. Okay, sorry, I jump one step. So if you just hit substitute here, you can get this one, but it's still not good looking enough. And we notice that if we this is 1 over Z here, and this is Z. So if you do the natural log differentiation, you can directly get 1 over Z and a Z differentiation. So that's how we end up here. Okay? natural log z partial t and with constant v. Okay, so basically this one and that one are the same. Okay, but this is better look. Better look. Okay, so u now become better, and give function is our next target. So give function for single component system is g equal to mu n. That's what we know that, right? And we also know mu equal to this one from the previous page. So it's easy. So g equal to, so you can imagine that when you start from the begin with s, and then you can have u, and then you can have everything. Okay, minus nkt natural log z minus natural log n. That's it. 好，现在要解释就是继续把 partition function z 发扬光大，把它连接到我们既有的材料性质。那材料性质我们可以看到我们的 internal energy 刚刚算到一半，然后觉得虽然好像不错，但是很丑。那怎么做呢？我们就开始去比较一下哈，这个东西长得很像我们的 z， 但是唯一的差别在于这边多了一个 epsilon j 在前面。那要怎么做呢？直接做微分就好啦，它就会跑到前面去 epsilon j 就跑到里面去啦。哦，那好，那接下来我们要做微分，可是呢，我们要做微分，我们不希望节外生枝嘛。哦，我们知道 z 是 v 的函数，但如果今天我们的 v 会改变啊，我们做微分 t 的时候，就还要对 v 来做微分，所以说我们就定 v 是常数就好。那这样子它微分才不会 v 跟 t 的关系还要再被微分。好，那所以我们今天就做了一个微分，然后在 v 的状况下是常数的状况去做微分，我们就可以很简单的把 epsilon j 移到前面去，然后我们可以得到这个红色波浪状的这个 term 跟这个 term 是一样的，我们就可以直接把这个东西带上去了。哦，当然是把这个东西弹过来，然后再把它带上去。好，带上去得到这个式子，虽然还不错，但是还是没有到很完美。好，那要怎么做呢？那其实你看到 1 over z 跟这边的 z， 其实就等于 natural log z 的微分啊，所以我们就再度把它精简成这样子，所以我们的 u 就可以长得比较更漂亮一点，写成在红框框的式子里面。当然啦，这边跟这边是一样的数值，只是你多算一下就变这样子了哈。好，那 u 写出来了 ，give function 是我们下一个目标。那我们知道 g 等于 mu n 嘛哈，那很简单 ，mu 已经被算出来了，乘上一个 n 就了结了。OK， 好，就这样子。下一个 ，so you can see that these 3 pages we just do a similar thing. We use classical thermodynamics theory and connect just using z to represent all the material properties. We know that, right? Okay, so next one is enthalpy H. Enthalpy H, as we know, H equal to U plus PV, and G also equal to U minus TS plus PV. So we can have H equal to G plus TS. Okay, and then we have S equal to U over T plus NK natural log Z minus natural log N plus 1. And then we just derive U equal to NKT squared partial natural log Z partial T over constant V. So if you have U and S, and then you can rewrite actually it's like this, right? Okay, so and then you can have H equal to blah 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 blah, and then luckily okay, and then you can have H equal to NKT 1 plus T times partial natural log Z partial T V. Okay, that's it. So this h equal to 差一点，嘿，不好意思啊，嘿，好 ，OK, so h equal to that. So when you have h, it's easy for us to, I mean, if you have f, h, g, mu, and u, okay, so you have plenty of all the stuff, you can using other relationship to obtain whatever you want. For example, pressure P, according to table 8.1, reciprocity relationship, which is minus f partial f over partial v. So you can get equal to nkt partial natural log z partial vt. Okay, don't forget the f equal to minus nkt natural log z minus natural log n minus plus 1. Okay, and again, the f may be different. If you apply to different statistics or distribution. Okay, Fermi direct, Bose-Einstein. Okay, they may be different. Okay, they may be different. So again, if you have this f changed, your p also changed or not, I don't know. Maybe after their differentiation, they will be the same. Okay, you can try it at your home. Okay, well, you notice that maybe they will have this or other, and if after you do the differentiation, the pressure will be the same. Okay, so in the textbook, I remember that the textbook mentioned some of the properties in different distribution, they are the same. They just mentioned that. The textbook only mentioned that, but they didn't emphasize that other may different. Okay, so this is really dangerous. So I don't know why these textbooks kind of try to, fool us. I don't know why I don't know why the author don't say it explicitly. They just say, oh, some of them are the same, and then it just said. So I kind of, I don't know why they're trying to do that. 好，接下来也是很简单了哈，这三页都很简单，我觉得第七章蛮简单的哈。第一章就是反正就把我们的已知的东西做出来，然后把这个带进去，然后得到这个东西，好，很简单，超简单。然后呢，我们又可以用我们第8章学到的东西，再从 P 开始，不是 P 开始，我们从 F 把它写出来以后做微分，就可以得到 P。好，那这边呢，我还是要郑重的提醒大家，这边的 F 是因为 Maxwell-Boltzmann 才写出来的，所以说不同的 distribution 会有不同的写法。那这时候又很有趣哦。这时候如果你做微分的话，好像我记得印象中好像其他的就是这个常数会不一样或什么的，然后做微分以后反而就一样了。那课本有一个很酷的地方，就是我不知道他为什么要写的这么，他有一个地方就是说，虽然就是那个虽然 distribution 不一样，但是在某些状况下，什么某些的 material property 就会一样。可是问题那是因为那 material property 是微分过后的啊，那不代表其他就会一样哦。所以他的课本，我记得印象中就是课本，我在第一次念这课本的时候，我有被误导，我说哦都一样啊这样子，但实际上不对，他只是告诉一些特例，跟你们说这些特例会一样，但实际上大部分的状况都不会一样，哦，所以这边要小心哈。对，我就觉得他很奇怪，为什么不好好讲？他为什么要讲特例，然后不讲一般的状况？我觉得有点怪。好，就是这样。他好像想要试图去，他好像想要让这件事情变得看起来很简单啊，但是我觉得这样不行啊，你要让大家知道真实的状况啊，对不对？我不知道啦。对，就是这样。Okay, next page. Actually, we have done that in similar to what we done in the first page today. Okay, so partition function z for a guess, maybe just for ideal guess, for an ideal guess. Okay, because we are trying to fit the Maxwell-Boltzmann distribution, right? So ideal guess. Right, so let's take a look. Let's take a look of the behavior of partition function, but actually we have done that. The only reason I put this page is because the textbook also mentioned this. Okay, so I just follow the textbook. When we have the z, okay, we can write it down like, we can simplify z into this formulation. What does that mean? Firstly, we assume Gj equal to 1. So we assume all the degeneracy is 1. Okay? And the ground level, the epsilon 0 is 0. To make it, you know, more simple. Okay? Simpler. Simpler. So if you assume this, you can rewrite z equal to 1. And that. So you make it every energy level as one term if you assume this. Okay? So it makes everything kind of, you know, separated and easier for us to understand what it will be look like. Okay? So the partition function is a measure of a state available for the system. Yeah, we mentioned that before. And the distribution gives mj is proportional to the exponential minus epsilon j over kt. Okay? Yeah, because mj equal to n over z exponential minus epsilon j over kt, and when gj equal to 1. Okay, so this is not the real case, but we want to make some, you know, simplification assumption to make us to see the distribution, meaning of the distribution. And as you can see, if we have this, you can kind of normalize this. You can make the lowest energy is 1 for the lowest net energy level, to make this exponential minus epsilon j over kt as 1. Okay, so it can kind of normalization to help you to understand the function behavior. Okay, so yeah, if you have the, and also we mentioned that in the very beginning of today, I said when we plot the curves, which means that we set the particular value of temperature. We are not discussing temperature variation in single plot. Okay, so you can see if you have low temperature, it will looks like that. If you have a high temperature, it will looks like that. Okay, so when you plot that curve, the temperature is actually set. Okay, that's the point that I stopped early 1 hour earlier, right? Yeah, so you can imagine that the first term is actually this one, and the second term is for that one. So you can imagine that one term for one point of the curve. So one term is this one, is actually this one is that, and you can imagine that lower temperature, the curve looks like this, and we will have a temperature, they will be excited, they become higher. Okay, so the population of the particle excited to the higher state, and then you have, if you have lower temperature, the particle tend to dense in the lower ground state, lower energy state. Basically, this the key points in this page, you already know that. Okay, and we mentioned that in the other pages. PDF 7 is really easy. 好，这一章其实根本都讲过了哈，那只是原因为什么要学出来，是因为我们书上本来就有写，所以讲说好了，那我就照着它的逻辑去继续走吧。那我们去看一下 partition function z 它的行为是什么。那实际上这边我们之前在刚刚那个也讲过了哈，但是就在就是我们今天今天上课的第一页，就是我卡住那一页了哈。好，那我们来看一下哈，就是说 z 它这样写出来，那我们想要看它的行为，我们就做了一些假设，让它变得比较简单一点，就让它把它定一个位，定一个位啊哈，就例如说 epsilon 0等于0，就是把它定在这个原点上，然后我们就不管它的 gj 是多少哈，反正就先假设为1好了，这样会看起来比较简单，让我们可以知道它的整体的行为是什么。我们先不管有多少选择啦哈，就当做是一个非常简单的材料。那来看看这个线会有什么样的行为。那我们假设这两件事情会有什么样的状况呢？会把这个 z 呢写成比较简单 ，z 会等于1加这个加这个加这个加下去。好，那每一项就是 energy level 0、energy level 1、energy level 2的贡献的意思。那 z 当然就全部都是加总起来，所以它是 all the available 全部可能的状态加总。那这也是我们之前学到的 partition function 的定义嘛，对不对哈？好，也就是第1个、第1个、第2个 energy level 的状态。好啦，那我们就可以画出来。那我们就会知道 NJ 跟这个成正比哈，这个我们也知道了哈，因为它写成这样子。好，那接下来我们我刚刚不是有卡住嘛哈？卡住我们想说，为什么 temperature 好像会变感觉？其实不是，我们在画这种图的时候啊哈。当你画出这条线的时候，你的温度就已经定下来了啊。应该说你定了温度以后，你就可以画出这条线。那这条线，如果高温的话会这样，低温的话会这样，但它长相都会类似啊，长相都会类似。那所以我今天早上在卡住的地方，就是我以为温度在同一张图里面还会变，不会，同一张图里面温度已经不会变了啊，因为你那个 distribution 就是在那个温度下的状态。好，所以说，刚刚早上我卡住的原因就是这样。好，那就提醒大家不要再跟我犯一样的错误了。那总之呢，第一个，energy level 的状态就在这里，那就是黄色这条线的值，然后蓝色这个值在这里。好，然后只要是0，就是 energy level 0的话，就是1开始。那我们就可以看到，就相对来说啦，哈，相对来说，高温的话，你就会比较多的比例。会跑到高的能阶上，其实我们也都知道了。好，那基本上对，就这样而已了。好 ，next one example of ideal monatomic gas. 好，so let's take a look. Let's apply this to a real macroscopic situation. We have a container for the macroscopic size, great size, big size. You can see that in the real world, okay? The energy level can be regarded as continuous. Of course, imagine that the coffee, right? We mentioned the coffee in the PDF 5, maybe. Imagine that the coffee has if the coffee is really tiny, really small in the quantum state, quantum level, they have a certain level of temperature. But if you have a normal size of coffee, you have continuous temperature. So which means that if you have a macroscopic size of container, which is always the case, right, can be regarded as a continuous energy level. And the density of a state can be used. Okay, what does that mean? Which means that we can rewritten the z, summation of z become integration from 0 to infinity. Okay, and okay, again, also available degree of freedom in the ideal monatomic gas is the translation only, right? So because for diatomic, we have more degree of freedom, more DOF, right? And which is rotation and vibration. But here we are not going to talk about that. In this page, we will talk about that later. Okay, but now for ideal monatomic gas, you only have the degree of freedom for movement, translation. So it will relate it to velocity, direction, or half mv squared. Okay, so something like that. So we only discussing translation. Our z equal to this one, no problem. That we mentioned that before, and we can approximately because now it becomes continuum, so it becomes 0 to infinity integration, and exponential, no problem. But g here is not gi, it becomes g epsilon as a function, because when you do the integration, you specify g by specify certain energy level. But certain energy level also corresponding to certain energy. So if you specify energy, you can get specified G, right? So your G is a function of energy, okay? G function of energy, and G function of energy, the epsilon, okay? So that's the reason why we're going to do the summation become integration. So we can have the epsilon in the back of in the end of the formulation. So we notice that we know the translation G epsilon, D epsilon, right? We have particle in the box. I mentioned that in my video, right? So G epsilon, D epsilon equal to blah 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 blah, ugly. And maybe you notice that this is a little bit different here, because there's no gamma S. No gamma S. You remember the equation, right? In the PDF 5, in the end of PDF 5, right? But why there's no gamma S here? It is because here, since the gas we consider is molecules, not spinning particle, not particle with, oh sorry, I should rearrange a bit, otherwise the grammar is not perfect. With half spinning particles. Not the particle with half spinning. Okay, remember when we talk about the particle in the box, right? We said, okay, particle in the box, when they move in the containers, they have a certain behavior like this. Degeneracy looks like that. However, at that time, we talk about quantum particles, right? The quantum particle may have half spinning, right? Half spinning. But now here, we still talk about the molecular movement, but not talking about the particle with the spinning. So we don't need that gamma S. Okay? So we just reuse that, but we don't need gamma S at the moment because we are talking about the molecular rather than the quantum particles. Okay, and then if we just substitute this to here, and then we can use a lot of ugly calculation, blah 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 blah, and this one, wow, looks terrible. But don't worry, because we have smart, clever mathematician, scientists in ancient age, so they have the gamma function, page 408 in the textbook, and then we can solve this easily. Okay, but oh, by the way, you notice that the epsilon is now become here. So I just want to emphasize that before we apply gamma function, we need to do the changing variables. Changing variables is a kind of important variable, technique in the calculus, and you need to practice this techniques for later use. So I just mentioned this to you to let you know you need to review your calculus, otherwise it will be used in a later PDF, okay? Later chapters. Be careful, okay? Then, 50. And then it becomes V equal 2 pi mkt h squared 3/2. Okay, so the important thing is that z is proportional to v. Okay, so that's the thing we mentioned last few weeks, I guess. I said, oh, I will explain this later. Yeah, here's the later. Right, so 10 minutes later, 等一下，没有，还可以继续上。Sorry, no, okay, let's continue. 哈哈，好险。Okay, good. So, yeah, I can translate now. 好，这个就是继续啊，我们要把就是刚刚partition function 继续就是应用下来。那这时候就开始 apply 到真实的相对真实的世界巨观上了。巨观上我们要看的是 ideal monatomic gas 是最简单的状况，就是它只有考虑 translation 这个 degree of freedom。如果是 diatomic 的话，就是双原子的话，那它就会有旋转啊、振动啊，那个我们先不考虑的话太难了，等下之后再考虑。那所以我们就只有 translation。好，那我们 translation 的话呢，先不管，我们就先管它的 z 好了。那 z 会长什么样子呢？我们想看看，在 ideal monoclinic gas 的话，它的 z 会长什么样子，而且在巨观下。好，那我们的 z 呢是长这样子，是之前几页我们就推导出来的。当然了，这个 beta 其实就是你也知道嘛，就是那些什么 over kt 之类的东西。好，那接下来我们写完这个以后，我们就要想，因为它是巨观，然后我们的 energy level 因为很多层，然后它又是 closely packed， 就是叫什么？紧密堆叠的哈，靠得很近，所以我们在巨观来看，它就是一个 continuous， 它是一个连续的一个变化。那所以 summation 就可以把它写成积分，加总就可以变成写成积分。好，那积分就把它写成这样啦 ，epsilon b epsilon， 不对，讲错了 ，exponential b epsilon 乘上 g 函式。这个 g 函式什么意思呢？你可以看到 gi 其实是第一阶的 g， 第二阶的 g， 第三阶的 g。好，那你可以想象在连续的状况下，我们要怎么样去找到那个 g 呢？其实我们只要指定一个能量，我们就可以找到 g 耶。为什么？因为原本的 g 是跟着能阶跑的，第一个能阶，第二个能阶，第一个能阶的 g， 第二个能阶的 g， 第一个能阶它有自己的能量。第二个能阶它也有自己的能量，所以你其实只要指定这个能量就可以找到这个 g， 所以它是1对1之间的关系。所以我们的 g 可以写成我们的 gi 在积分的时候就可以写成 g epsilon 的函式这样子。好，那我们就会发现啊 g epsilon 函式 d epsilon 这样写出来了，要怎么办呢？要怎么积分呢？好险我们在 particle in the bus 那个就是颗粒在核中的颗粒这个 case 里面有算出这个东西算出来了。但是呢，大家可能会觉得，为什么没有 gamma s？ 我们那时候结果不是算到后来就会有 gamma s 吗？那 gamma s 其实是给那个 particle 有那个什么旋转的自旋的那个1/2自旋的那个。但是我们现在是分子没有这种自旋，所以我们就可以不用管它，我们就可以不用写那个系数了，这样子。好，那所以我们就把 gamma s 拿掉，就是这个东西拿掉，这个东西拿掉。好，拿掉以后呢，我们就可以直接应用在上面，而且这个东西是 translation 嘛，particle in the bus， 在它移动来移动去这样子。好，我们把它丢进去了，积分，好恐怖。积分到后来呢，我们就会遇到这个问题，好难哦。不过 天才的科学家有算出伽马方程可以帮助我们解这个东西。那我就略过了哈，太难了。不过这边有一个东西要提醒大家，就是我们在使用伽马方程之前，我们要先把 d epsilon 呢改成这个 epsilon 除以 kt。学过微积分的知道叫做变数转换嘛，对不对哈？那为什么忽然提呢？原因是因为之后你要常常用到哦，尤其是PDF 8跟9哦，会用到这个，所以请大家就是趁现在还没有到的时候，赶快去回想一下，温习，重新捡回你的微积分的技巧，好技巧哦，好难哦，就是我现在脑袋就是一直英文中文的那边转换，就不知道如何选字，有点困难。好啦，总之就是这边要小心。好，那接下来呢，有了这个算完，就是 apply gamma function， 就是应用这个 gamma， 不能说应用，中文那怎么翻译啊？就是使用这个 gamma function 的话，就可以解出来了，解出来以后就带回去，就可以得到这样的式子。那重点在于，就是说 z 在 ideal monatomic gas 的时候，它会长这个样子。好，你会发现哦 ，z 这就是常数嘛，所以 z 真的跟 v 是正比的。那还记得我们那时候是 z 正比于 v 的时候，我在前几个礼拜吧，有写说 z 正比于 v， 然后为什么呢 ？explain later， 就是我们之后才会讲到，这就是现在你看到，对 z 真的是会正比于 v， 那就这样，好，结束了。Next one. So for property of a monatomic ideal gas, if you have a z, again, if you have z, every material property mentioned in classical thermodynamics can be written by z. So that's the reason why z is so important. Okay, so z equal to blah 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 blah, and then we can start to get the mu, u, s, f, p, everything. Okay? And you notice that a lot of place we need natural log z. So if we have z here, we firstly you just get natural log z equal to 3/2 natural log t, natural log v, 3/2 natural log 2 by mk h squared. Okay, so natural log z looks like that, and you can apply to everything, blah, 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 blah. Okay? And then you can get and then you find that p equal to ideal gas law. So you find that, okay, you're using different approach to get the same result, which means that they agree with each other, which means that the both approaches are correct. Good. And please verify S here is equal to minus partial f over partial t, and p equal to this one. Okay, you can verify that. Go back home and do the work to examine each other, and then you will find they are really matched. Very good. 好，那有了 z， 刚刚写了 z 了，帮 monatomic ideal gas 单原子的理想气体，帮它写出了 z 以后，哇，那你就赶快把它全部 apply 到你知道的东西上，然后你就可以得到这个式子，这些式子，哇，好多，而且其中一个还是 ideal gas law。好，所以你会发现，你用不同的方法还得到同样的结果，表示说这两个方法都是对的，真的是所以说，爱因斯坦才会说，这个永远不会被推翻，因为你怎么做都是对的，好厉害这样。那请大家回去就是做个实验自己去做一些微分、积分，然后去看看他们之间的关系是否正确。那通常都是正确的如果不正确，它表示你算错了。OK， 大概是这样子。By the way, this is a Secker-Tetrode equation, and then we will use that in the next few pages OK， 不是 next view， 下一页，我们下一页就会用到这个东西，它叫做 Sacher-Tetrode equation。OK, good. Now, the next we are going to use Sacher-Tetrode equation and to, examine this entropy. So the entropy for a monatomic gas, you can see this one, ugly, but you see, indeed, in our classical thermodynamics, we found that the S is a function of temperature, number of particle, and volume. Yes, indeed, they all include in that equation. And then we found that we are going to have a break, and then I will see you after 10 minutes. Thank you very much. 喂，Hello。对，我发现就是只要可以上传，停课的时候上传影片，这个就是让我觉得非常的轻松，然后我就可以跟大家聊一聊我想要问的问题。我最近有一个问题想要请大家，就是如果知道的话告诉我，等一下下课可以告诉我，或是你可以，现在也可以讲。总之就是我最近想要买一个，我最近想要买一个 iPad 的懒人，就是不要用手就可以在你前面那种，这样有这种东西吗？然后我不喜欢那种，我之前有买过夹的，但是不是每个地方都可以夹嘛，而且夹都会让那个家具破坏掉，所以我想要有没有那种是立着的吗？然后这样子的，然后就可以不用手拿，然后就可以看 iPad 这样，有这种东西吗？好，有同学点头，很棒。但是我不想要用夹的。我刚刚讲说不想要夹是这个夹，但是我现在我也不想要夹在 iPad 上，因为它有很大的力气。好了，我直接讲啦，其实是要买给我妈的啦，因为我妈的手没有力气比较小嘛，但是她又要拿着 iPad，她现在是低头族，所以她就我想要用磁吸的，磁吸然后站着的，有这种东西吗？我上网查好像没有查到。又或者是说我可以先买一个站着的，然后再把那个头改成磁吸。所以看有没有各位同学有没有这样的经验，可以让我就是对，就是有没有这种建议？拜托，如果知道的话就告诉我，我不会帮你加分，对不起。但是但是请告诉我。对，就是我上网去找，而且你知道我甚至有去找过，就那种 L，因为是我妈要看嘛，所以老人家嘛，就是手没有什么力，然后老花眼或什么，想要用大的。我甚至有去就是搜寻那个 LG Stand by Me， 你知道？那好像什么闺蜜机嘛，我不知道，反正它就是一个很大超大的荧幕，然后可以移动来移动去。但是我后来发现它只能追剧，它就只是个电视而已。那好像不能去打字，因为我妈就是长辈图嘛，要传赖啊，要叫回讯息啊，所以我也希望是能打字的。所以那个大荧幕的 LG 那也不是我的，就不是我想要的了。那所以就想要说，还是回归到就是买一个好的就是直接吸附上去，然后手机也可以吸附上去。因为我之前买了一个夹的，然后我就把它夹在他的椅子上，夹在他旁边的桌子上什么的。但是他因为那个是要用搬开的，然后就是手要很大力，然后把那个手机跟 iPad 这样放上去，然后再夹起来，然后他就不想用了，所以我就白买了。那如果今天它是一个立的，它可以直接搬来搬去，然后又可以是用磁吸的，还可以吸他的手机，也可以吸他的 iPad， 那真是太棒了。有这种东西吗？啊？什么价？乐谱价？哎，好像蛮不错的哦。可是乐谱它会这样子吗？它会有，因为是坐着的嘛，它放在旁边，它就不能，它就要这样看啦。如果是乐谱架，它是直立的，它有没有一个 bar 是转弯到你面前，是可以这样看啊？还可以加是乐谱，搞不好是乐谱，它就是一个像书架一样的东西，搞不好不错。嗯，还有没有？赶快想，如果你有那个的，就是心中有想法的话，赶快传讯息给我。OK，寄信给我也可以。好，感谢，我会非常感谢你，但是我没办法帮你加分，对不起。网络上的同学也可以告诉我。好，要用英文吗？Recently, I tried to buy a stand for my mother because she wants to. She always look at the iPad, but her eyes and muscle are not good. So I want to make her comfortable, right? So please recommend me a nice stand which can easily put iPad or iPhone on it, and she can just sit on the couch, anything, chair, and then just see the iPad. Yeah, that's it. Okay, thank you. So let's continue. The entropy of the monatomic gas Sackur-Tetrol equation, we just derived from the entropy, the Z partition function. And then we can have this one, no problem. And then we found that some of them are constants, right? Some of them constant. For example, NK 5/2, natural log 2 by NK and H. Okay, so we notice that we can simplify this equation into S0. The S0 is this one. And then the rest of them will be NK 3/2 natural log T plus natural log V over N. All right, so S0. You notice that we name it S0. So it's actually related to when temperature become absolute 0, which means that you have entropy at the really low temperature. Okay, so actually the S0 is undetermined, cannot be determined in the classical thermodynamics, but now you can obtain by this one. So that's good. By measuring the CV and T. Why? Because if we just divide all these variables by n, and then we can get, so for example, if we just divide S, small s is S over N, R equal to NK over N, and CV equal to 3/2 R. So if we have this, we can rewrite the above equation become S equal to CV natural log T plus R natural log small v plus S0. Okay, so everything divided by kilomole M, and then you can get this. So you notice that, yes, this is CV, this is temperature, and volume, and R. So they all can be measured in experiments. So if you can measure that, you can determine the S0, and yeah, so that's quite nice. But still, this is not perfect, because this is always, I mean, theory always has some assumption, not fit all the conditions. So, however, if you can notice that when temperature going to 0, approach to the 0K, going to the 0K, and then the S0 become non-zero. Sorry, S0 become non-zero. But remember our last slide, before our midterm 1, we just say the S0 equal to 0, right? So still not fit perfectly, but well, this is just a measurement. You can see the relative value of the S and S0 in different case, right? So it's not always true, but useful, I guess. 好，那用Sackur-Tetrol 的方程式呢，我们可以写成这样子，然后我们就会发现里面有一大堆是常数，那我们就把它取名为 S0。那 S0是什么呢？其实基本上就是我们每次之前的积分的那些就是叫做什么反正就是它的常数就对了哈。那个常数通常是我们以前在 Classical Thermodynamics 传统热力学的时候，我们只能算出 delta S， 对不对哈？但是在这里我们就真的可以算出一个值来了。我们就真的可以去量它的 CV 跟 temperature 来，但是 CV 跟 temperature 怎么来呢？其实就直接把这个 S 啊、R 啊、CV 2/3 R 这边写出来以后，就可以把上面的式子写成除以 n 以后就可以得到这样的式子了。OK， 然后我们就可以用这样的方式去量测这些值，然后算出它的 S。OK， 但是呢，虽然它有好处，可是问题是当它在 t 等于0的时候，0k 的时候，它的 S no 就不为0啊，对不对哈？不为0嘛，对不对哈？那但是又跟我们我们在第一次期中考的最后一页的期中考之前的最后一个投影片，我们不是说entropy 到0的时候 S no 是0吗？哎，那这样就糟糕啦，怎么又不对呢？其实所有的那个什么理论哈，人类提出的理论都不会全部都符合啦哈。那所以说就会有一些假设嘛，对不对哈？那所以不是对，所以就只能是说我们可以去看大家的相对值，就是可以用，但是不一定每个状况都会正确。这个东西对于你看这个 CV， 其实CV 等于这个3/2R 这种东西在之后我们也会提到，就是在低温状况下的时候它就会不准所以这就是人类去试图去写出一个式子，然后得到的结果，但终究不会是完美的。好，那我们之后也会提到类似的事情。Okay, next. So now let's take a look. Maxwell-Boltzmann distribution. We using Maxwell-Boltzmann distribution to calculate a lot of material properties. That's good. And how good is the Maxwell-Boltzmann distribution? Is that really reflect the fact that ideal gas is dilute? Is really that case that NJ much less than GJ. We want to see if the Maxwell-Boltzmann distribution is good enough to describe this feature. Okay, so let's take a look. So Maxwell-Boltzmann distribution valid for dilute gas. Is that true? Is that really good to explain, to describe this kind of dilute gas? Can we do that? Let's take a look. NJ over GJ equal to this one. This is Maxwell-Boltzmann distribution, no problem. And then the Z here, the Z here is here, and that, right? Compared to the, well, I can give you, Okay, so yeah, you can notice that we obtained from the previous page, and then we can get this ugly term. Okay, so let's take a look if this is correct. Let's continue. Not correct, not good enough. N over V, and we simplify then. It's become NQ and exponential minus J epsilon J KT. Okay, now NQ, what is NQ? NQ is 2 pi, again, this is constant, ugly constant, H no, and 3 over 2. And it will be become 7 times 10 to 30 m over this one. Okay, how? It comes from here. Okay, so let's take a look. Wait a minute. Green. Okay, NQs come from this one. So let's take a look. After we have NQ like this, and then we need to apply to a real case. So taking helium gas on the STP, this one, and this one is STP, right? Standard temperature and pressure as an example. M equal to this one because we're using helium gas as an example. We have all this and we substitute this as NQ. So for this case, helium under STP, we have NQ relatively approximately 7 times 10 to 30 m over 3. That's m2 minus 3, sorry, m2 minus 3. Okay, so this value looks like that, no problem. Then, how can I do that? Okay, and then MV is this one, okay? MV can be determined 6.02 10 to 26, sorry, over 2.2 4.1, and then you can get this one. Okay, so I shouldn't, sorry, I prefer to draw this. MV. Okay, last part is what color? Purple. Okay. Pink. So this one. Okay, this one is the remaining thing. What will it look like? So let's take a look. Now we can have a figures x, exponential x, 1, 2, minus 1, minus 2, 1, 2, 3. Okay, and then exponential x will be looks like that. All right. Exponential x looks like this. Okay, along with the x. Now, you notice that this part is actually this part. Why? Because it's minus. It is minus, right? So minus epsilon j over kt, the x here, the x here, is always in this part. And what will it be? The epsilon over kt in here is in the order of 1. Okay, so we will say exponential minus epsilon j over kt will approximately 1. Right? You can see here is minus, right? So you can see exponential x, and with the minus value, it will always similar to 1, 1, 1, 1, 1, 1, or maybe 0.8, 0.9, but it's okay, just close to 1. So you can imagine here is 1. 1, okay? So here, right, so now you have yellow part, green part, and pink part, or purple part, anyway. So now you can approximately 3 times 10 to 25, and then divide by 7 times 10 to 30, and times 1. Okay, because they are all in the order of 1. So mj over gj will approximately 4 times 10 to minus 6. What does that mean? Which means that mj gj ratio equal to 4 times 10 to minus 6. So if you are kind of reverse it, you will find that in 1 over 4 10 to 6, if we reverse it, you have 0.25 million degeneracy, and only 1 state is occupied by the particle. Okay? So you just inverse this. You can have 250,000 and 1. Okay, their ratio will be that. So helium gas in the STP condition is highly dilute because 0.25 million to 1. So this is a normal condition, STP, standard temperature and pressure. And ideal gas is defined, so you can see that the reason why, the Maxwell-Boltzmann distribution does describe the dilute gas quite well. Yeah, 0.25 GJ and 1 particle. Yeah, that's good. So let me draw this. Okay, so I hope the color will help you to correlating all these values. 好，讲就是说 Maxwell-Boltzmann distribution 算了那么多啊，我就想说，Maxwell-Boltzmann distribution 真的 OK 吗？真的适用于这个就是现实生活中吗 ？O 不 OK 啊？那我们就要来应用到现实生活中的例子，来看它是否还维持它的假设啦，它的假设。好，那这时候我们就把 NJ over GJ 写出来嘛，然后这个 Z 呢，就是刚刚前面那一页这个，不对，这个东西，这个东西，好，那写完以后呢，不好意思啊，我再画一下哈，让你们更有颜色的感觉。OK 好，这边有蓝色的，好，然后你这边就是蓝色的。好，那有蓝色这边写出来以后呢，我们就一样把那个叫什么，这些很多这个叫什么，常数把它写成 NQ 啊，把它写 NQ， 把它写在这里，然后 NV 还在前面，后面这个东西在这里。好，那这时候我们就来看看啦，如果现在把它应用在现实生活中，假设啦，helium gas 跟在正常的温度然后压力的状况下。那它的 helium 的 m 是这个东西嘛，我们就可以把这个 NQ 算出来，把这个东西算出来是7乘10的30次方。好，7乘10的30次方做完了以后，接下来呢 MV 又是多少？反正它就是 STP 的状态嘛，你就算出来3乘10的25次方，这是黄色的这个部分。那接下来呢，最后这个部分粉红色的部分该怎么做呢？粉红色的部分呢，我们来看一下我们把这个东西写成 exponential x。我们把 exponential x 画出来，图画出来长这样子。好，那我们就发现这个 x 在这里都会是负的啊。epsilon j 跟 kt 都会是正的，所以说这一定加上一个负号就绝对是负的，所以这负的呢绝对都在后面。那所以前面我后面就不用管它了我们只要看后面，后面都会是这样子。好，反正它就是0以上1以下的东西。它就是差不多1啦0.8、0.9、0.7就是这样子了好，那反正我们只是要去看它大概的数字，所以我们就写成1咯。好，这边1，然后把这个3乘10的25次方除以就黄色除绿色就是我们的 NJ over GJ， 大概会是4乘10的负6次方。这什么意思呢？也就是说它们的比值是4乘10的负6次方，也就是0.25百万分之1啦，也就是说0.25百万个 degeneracy， 但是你只有一个 particle 去占其中一个，那果然超歹路的嘛，对不对表示说它还是有维持真实应用在真实世界上，对它真的就是保持它的假设，就是它歹路 gas， 所以还不错的意思。好 ，next one。接下来next one is distribution of molecular speeds. Now we are going to correlate everything with what we learned in classical thermodynamics, section 11.6. This page is try to correlate it to 11.6 section. Okay, so now for an ideal gas, Maxwell-Boltzmann distribution, of course. The speed distribution of the molecular for continuum energy level. Okay, let's take a look. we are going to see the molecular speeds, right? And then we are going to see the particles. Okay, the particle in the statistical thermodynamics will always correlate it to energy level. Energy level is epsilon. The epsilon here is actually half mv squared. So that's how we connect energy and velocity. Okay, so now epsilon has been correlated to velocity now. Okay, then let's take a look. We want to see how many particles for particular velocity, particular speeds, right? So we need to write down, okay, the Fj in the energy level, okay, is defined by Nj over Gj. That's what we learned, right? We know that in the previous few pages. However, because now because we specify energy level J means that we specify certain certain energy value, right? So which means that our F is also a function of epsilon energy. So we can say N and G are all function of epsilon. We specify particular energy, which means that we specify energy level, and we have the Gj or Nj. So they are all the same, just different description. They are all the same, right? So now, because we are going to talk about molecular speeds of the distribution, right? Distribution of molecular speeds. So N epsilon, D epsilon is what we are going to learn, and M epsilon equal to G epsilon times F epsilon. So that's the reason why we have this. Okay, now here become here, and then luckily the F epsilon equal to this one, no problem. So we substitute here to here, and G epsilon D epsilon, no problem. We just learned that. Okay, so then these ugly term Z here, okay, ugly term will become N epsilon D epsilon become this one. Ugly, very ugly. Okay, so how can we make it feel better? So let's take a look. Then we found that the epsilon are energy, right? But we know that we are going to correlate it to speed. So what is the energy level, energy and speed correlation? This is epsilon half mv squared. You know that, right? So epsilon can be replaced by half mv squared, no problem. However, epsilon to half, square root epsilon and d epsilon. How can we get that? It's okay. Easy. We can get this from okay, so you can have epsilon square root the epsilon equal to 1 over square root 2 and 3 over 2 v squared dv. Okay, by using the left hand side, and then we can have epsilon square root d epsilon. Yeah, d epsilon equal to mv dv, no problem, right? We just do the differentiation. So here is here, and this one is this one, and then everything here. We can substitute this one to the blue highlight part. Amazing thing happened. Okay, if you substitute this ugly term into here, and you obtain. Oh, now by the way, here is n epsilon as n is a function of epsilon, but now because you replace the epsilon become v, so now your m epsilon become mv, and your d epsilon will become dv. Excuse me. Then you can get this one. Wow, did you see that? Did you see that? This equation mentioned in chapter 14.21 equal to section 11, equation 11.28. They are exactly the same. So again, two different approaches, you obtain the same result. You prove that both of them are correct. Very good.好，这实在太厉害了。就是说啊，我们现在要回顾一下11.6章节，不好意思节。那想要看看就是在 ideal gas 里面的速度，分子的速度的分布是怎么样的？既然可以连接起来，你看我们使用的是 Maxwell-Boltzmann distribution， 对，我们是用 ideal gas， 没错。然后呢，我们就来看看它的速度。那要怎么样连接能量跟速度呢？能量就是1/2mv平方。OK， 好，那我们就来看看啊，我们的速度要看它的分布，不就是要看它在某种速度下有几颗嘛，对不对哈？好，那但是我们现在这个状况，我们目前只用 energy 嘛，哈，所以我们就先写 energy d epsilon 跟 n 是 epsilon 的函数 ，n 是 energy 的函数。好，那 n 要怎么写呢？还好啦哈 ，F 就是 NJ/GJ， 就是它的 ratio， 就是它的 ratio。这个 ratio 呢，它就可以写成原本是 FJ 定义成 NJ/GJ， 可是我们刚刚不是讲过吗 ？J 是一个 energy level 的数字嘛，对不对哈 ？energy level 1、2、3， 但是没有关系，因为你的 energy level 1就会有一个 energy level， energy level 1就会有一个 energy level 的值 ，energy 的值，2也有另外一个值。所以等于是说，你指定这个值的话，你就对应到这个 energy level 的数字嘛，所以说，其实你只要你的 F 还是 energy 的函数，energy level 的函数，那 N 也是一样 ，G 也是一样，你指定一个值，你就可以知道它那个 energy 的 particle 有多少个，然后 G 有多少个。好，那你这边 F 就可以把这个东西写成 epsilon 的函数了。那我就把 n 取代成这样子。那很高兴的就是，幸运的是 F epsilon 跟 G epsilon 我们都写过了，所以我们就带进去以后得到右边这个丑丑的式子。丑丑式子这边epsilon 可以被换掉。那黄色这边怎么换呢？其实很简单，就是 epsilon 等于2/mv平方就好了，直接带进去就可以了，没有问题。但是剩下的这个蓝色怎么办呢？没关系。我们用这个东西的话，我们做一个微分，就可以知道 d epsilon 其实等于 mv dv，no problem。其实也算是一种变数转换了哈。然后呢，根号的话，当然就根号很简单，算完以后把它乘起来以后，得到这个丑丑的东西带回去以后，神奇的事情发生了，把这个东西带回去以后得到这一个式子，这个式子是14.21式，但是跟11.28式是一模一样的。我们用 kinetic 推出来的式子。跟用 不好意思，动力学推出来的式子，跟统计力学推出来的式子是一模一样的，太厉害了，证明两个都是对的。Next, the result for V and result for Vx. Remember that the V here is for all the direction, considering a ball grow, right? But the Vx is considered 1 degree of freedom only, one direction only. So we are considering a plane move from minus infinity to infinity, okay, positive infinity. So remember these two things we discussed in PDF 4, okay? So if we want to use mv/dv for 1 degree of freedom only, and then we can write m as function of vx dvx. And then yeah, we just write it down like here. And then you see half mv squared, right? But now the v squared become vx squared. Again, because it's not necessarily vx, it could be vy, vz, or any other 1 degree of freedom. So in the textbook, they try to write it down as general as possible. Okay, so it said in the textbook it said epsilon z, and this z is not partition function. Okay, it's yeah, it's a kind of symbol for 1 of the degree of freedom. Okay, so that's the reason why I wrote it. How about write it smaller and more wiggle? Okay, so now because they are trying to, it's not partition function. We need to be really careful. So I really don't like the way they present in the textbook. Yeah, so for example, A E minus epsilon Vx over KT D. Although I understand why they do that, but it's still kind of confusing. If they just write down like this, we understand, oh, this is for Vx. But for the book writing, maybe you need to write it as general as possible. So that's the reason why they use Z. And the Z here is the number of a molecule with the parameter Z. The Z here is just 1 of a direction or 1 of a degree of freedom. Okay? Yeah. So the epsilon bar as a function of Z. The Z is a degree of freedom, 1 of degree of freedom. Okay? The symbol. Then you can notice that epsilon z is also az squared. So basically, you know what that means, half mv squared, right? So I don't know why, but and of course this is a quadratic function because half mv squared, right? And then so we can write it down the epsilon bar z. It is the average energy of a molecule. Okay, the average energy of 1 single molecule. Okay, in that direction, 1 particular direction. So it should be U divided by N. And U here is all the summation epsilon times N and divide by total number of N. So here is, this is 1 particle. And N here is how many particle in that particular direction z. Okay, so it's a little bit complicated. So you are trying to get the 1 degree of freedom, okay, along that direction, the z here, and you can have that kind of amount of particle, and that epsilon z is one particular one particle's energy, and then you time them together and do the integration, divide by entire number of n. So you can actually, this is expected value, right? Expected value okay, of course this is expected value. So amazingly, this ugly form, oh, by the way, you need to substitute this mz to here, okay, and then this here, and the epsilon z is az squared. You know, this is half mv squared. So every number here already, and you do the integration and do the calculation, you can obtain a really simple result. Half kT. Okay? So for energy, for each degree of freedom. Okay? And then it also agree with what we learned in classical thermodynamics, F over 2 kT. The F is the number of degree of freedom, right? Remember that, right? Okay, so again, matched. Okay, 好，这一页我觉得有点麻烦了哈，但是概念是简单的。还记得我们之前有做 v 跟 vx 的差别吗 ？vx 是球嘛，对不对？哈，长大，球变大，是从0到无限大。但 vx 的话是从速度是从只有一个方向，从负的无限大到正的无限大，所以它的式子会有点不同哈。好，那这时候我们想要看一个 degree of freedom 会怎么样？那一样，我们就写 nvx dvx， 然后把它写出来哈。那我就是把这边拿下来写。那要怎么样把它写成就是能量关系呢？哈，能量关系，那我们就把你可以知道这边1/2 mv 平方就是我们的 epsilon 哈 epsilon 括弧 vx 这种感觉。可是呢，课本就很喜欢写的比较一般性，就是要写的都对就对了，你不能只写 vx， 那这样他可能会认为我们读者会认为是vy vz 不算没有，其实是 vy vz 也算了哈，所以说他这边就写一个奇怪的 z 符号，但是又很容易会跟我们的 partition 方程搞混，所以就觉得有点麻烦啊。总之你会发现我这边的 z 就写的像是就怪怪的哈，跟之前的 z 是不一样的。好，那总之这个 z 呢，其实就是这个奇怪的 z 呢，其实就是我们的 vx 或 vy 或 vz， 等于是一个特定的方向就对了。好，所以我们的 nz 底 z 会等于写出来这样的式子。好，那这边的例子就是其中一个就是 vx。好，那我相信大家都可以理解这在课本在干嘛。好，那接下来我们也可以知道 epsilon z 会长什么样子，那就是1/2 mv 平方嘛，对吧 ？vx 平方。那这个只是把1/2 m 写成 a， 好，那 epsilon z 就是一个24的方程式，那当然大家都知道咯。然后 epsilon 当然是会跟 vx 的平方成正比，因为是1/2 m 嘛，对不对？哈。好，那这边有了以后，我们就可以去算它的平均的每一颗的能量是多少 ，epsilon 的 bar。好，那 epsilon bar， 那这个只要有 bar 就知道，就是说我们要去算它的能量，还有它的个数，再除以它的，应该说算它每一个能量的几率是多少，加总起来。那怎么算呢？就是上面就是能量乘上它的个数，再除以它的总 total 的个数。OK， 好，那一样，那就是那 expected value 哈，期望值。 那我们就算一下啊，算，我们就发现 NZ 就是可以直接从上面把它带下来，epsilon z 就是1/mv 平方嘛，哈，也把它带上去。结果呢，算，看起来很可怕，但是实际上算到后来，竟然会等于非常简单的1/kt。那跟我们之前学到的 classical thermodynamics 传统热力学算出来的东西是一样的，1/fkt。好，只要一个 degree of freedom 就是这个 f 就是1了哈。好，既然是这样，又很完美的契合了 ，OK。So next, entropy for change of mixing, it will be correlated to section 9.5. 9.5, okay. Again, this is very simple. Previously, our n is for kilomole, right? But now we are going to kilomole. This is kilomole. And again, initial state, N1 Tp, N2 Tp, after mixing, N equal to N1 plus N2, and T again, the same, P equal to P1 plus P2. So in classical thermodynamics, we have the result, delta S equal to blah, 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 blah. This is what we learned in the section 9.5. But in statistical thermodynamics approach, how can we see this problem? Okay, so actually in statistical thermodynamics, mixing is to increase the number of configuration available in the system. Okay, I don't know if I can make it fit in. No, anyway, so which means that you introduce more possible states for particle to occupy, more possible energy level for particle to occupy. Okay, so W is increased. Okay, so previously, so the delta W, so become you previously only had one choices, and the other now become more. So the delta W is previously you only had N1, the other has N2, but now you have total n factorial, which means N1 plus N2 equal to N. Okay, so you have more possibility. So the delta W will be n factorial divided by N1 factorial, N2 factorial, and N1 and N2 will be with the ratio between the N1 and N2. So total particle times X1, total particle times X2, and of course X1 and X2 are the ratio of the component. Okay, so yeah, the delta S equal to K natural log W, natural log delta W. So you can decompose it, and by using Stirling approximation, okay, and you can have exactly the same result like this. Of course, a little bit change n equal to nkr. Okay, so again, fit the section 9.5. Okay, I'm sorry that this is it's all for today. I didn't translate it, but I will record. My recording will help me to translate. Okay. Next week we turn to, and next week I will upload video, and it will start from here to chapter 8. All right. So if you have any questions, just let me know. Thank you very much. See you next week. Okay. Bye.
请修改。这边的。老师，我想问，这个跟这个是一样的？那这个是这个吗？
除以 n， 你要除以 n。
这个是这个除以 n。
对。
哦，
对，
好。老师，我刚有找到。
又错了吗？哪里？
我刚有找到这个。
哎呀，哦，好。
就是它有圆形的，然后如果是平板的话，有大的。可是我觉得如果大部分都是平板的话，就可以用这个。然后如果还要手机的话，就可以圆的。
但是我觉得这个可能比较好，因为它会伸出来，对不对？
这个对，这个对。
对，因为我妈是坐在这里，然后应该这样讲，这边它旁边有个桌子，然后就会坐在这里。那如果今天想要夹在这里，其实也有夹在这里。我之前就把它夹在这里，它就不行。那所以搞不好这个它可以放在桌上，但它可以转过来。
我觉得这个，它就可以放在这里，这个
我想它如果放在这里，它可以在这里的话，就会很棒。
我觉得跟这个，
我买过这个，它就不一样。
然后磁吸的，
对，不是磁吸的。夹的会坏，让那个桌子坏掉。
你不觉得这样子，然后还要放的很奇怪？
对呀。
那就没办法弹。
对啊，我也觉得，所以它这边要很重。所以我原本是想说，如果这边有一个很高的，
有那个，
然后
我知道
对
你在讲那个电池的那个。
对啊。
就可以让依赖。
对，但不过哇，这个嘿，怎样？你怎么那么强？等一下，我先把这个录影录掉，免得
找到再说可以。
好啊，麻烦你哦，真的这个。